Good evening, everyone. So it's been a wonderful conference so far. I've really enjoyed it, and it's a pleasure to be able to talk to you here this evening about some of the work I've been involved in, a topic I've been especially interested in for the past few years, and that is looking at the effects of ionizing radiation on superconducting qubit arrays, and in particular looking at correlated errors that can arise from these, and then trying to study ways that we can, mitigate these sorts of effects. And this is both work in my university lab at UW-Madison, and also some of the mitigation ideas come from the startup company that I'm part of, CoLab. Okay, so just to set the stage, a few years back, I guess right around 2021 or so, there were a couple of key experiments that showed that correlated errors were really a thing that people needed to be thinking about in superconducting qubit arrays. There was this nice experiment from the Google group where they looked at one of their 50 or so qubit array chips, and they were repeatedly measuring T1 at some cadence on most of the qubits in this array, and what they would see that there would be occasionally events where all of a sudden a bunch of the qubits would start to have really low T1s, and these would spread and take a while to cool off. They would take sort of more than milliseconds, many milliseconds to cool off. And these sort of events would happen maybe roughly once every 10 seconds or so. So that's a little weird, and that got people thinking about what's going on. About the same time, there were some experiments in Robert McDermott's group at UW-Madison looking at charge-sensitive qubits with different physical separations between them and looking at correlated charge jumps seen between the qubits. And they could see that qubits that were close together, like these down here, would see lots of correlated charge jumps. Qubits that were far apart would see very, very few correlated charge jumps. And this has been followed up by a series of papers. I can't cite them all here, but just in the past year, there was this issue came up again in the Google Willow experiment from last winter, where they showed as they look at their big qubit array, they're running error correction on it, as they would extend the error correction depth, they would see a floor in their logical qubit error rate. It should keep going down. That's what we need it to do. But instead, it would reach this floor here, and that could also be attributed to these same sorts of events that happened here. And so, what are these events? Well, the picture is these are coming from very high energy processes. So when an ionizing impact happens, something like, say, either a muon from cosmic rays or a gamma ray from just background radioactivity in the lab, when one of these very high energy particles strikes the chip, it's almost always, if it's going to strike the chip at all, it's going to hit the silicon, because that's, almost all of the volume is the silicon and not the thin film on the top. But when this happens, say a typical gamma ray hitting the chip deposits roughly 100 or 200 kilo-electron volts into the silicon. So that's an extremely high energy compared to the energy scale of the superconductor that we make our qubit junction on, which is an MEV, little MEV. So this is enormous difference in energy scales. But what's the cascade of processes here? Well, I'll talk through this for a few slides just to get the picture in your mind. What happens first is, say this gamma ray comes in and it ionizes the silicon. It makes a whole bunch of electron-hole pairs, tens of thousands of electron-hole pairs. Some of these electrons and holes recombine right away. Others of them spread out, and they eventually get trapped on defects in the silicon, either acceptor or donor impurities. And so that changes the local charge environment around the impact site, but also that motion of the electrons and holes and the trapping of them onto impurities, and the ones that recombine right away, all those processes radiate many, many high-energy phonons. These are phonons with energies far above the superconducting gap, and phonons, of course, can spread throughout the chip very efficiently at the speed of sound, and because they're above the gap, whenever they hit the top surface of the chip, where the junctions are, they break pairs, they break Cooper pairs, and make quasiparticle excitations, right? And quasiparticles are dissipative, right? They're these single particle excitations. They carry entropy when they move, unlike the Cooper pairs that are in this ground state that can move in this supercurrent without dissipation. So elevated quasiparticles are bad. They degrade the qubit T1, and that's why we need to understand them. Okay, so this is definitely an incomplete list here. So just highlighting some things that have been done over the past years. But yeah, this is the basic picture, and let's look at this in just a little bit more detail. Here's another way of visualizing this. The gamma ray, say, comes in, strikes the silicon, generates a whole bunch of electrons and holes that spread out a little bit. Typically, turns out to be, for a typical defect density in the silicon, they might spread out, say, a few hundred microns, maybe as far as a millimeter, before they get trapped. But then that radiates these phonons that spread throughout the entire chip. And so there's a bunch of different signatures, well, there's really 3 different signatures, that we can look for to try to study this process. So one thing we can do is try to use qubits as electrometers to try to sense shifts in the local charge environment. So we can try to look at these electrons and holes reconfiguring and see if we can sense when an impact happened and where it happened. That's one thing. But then the phonons, these pair-breaking phonons that are radiated throughout, that's going to, again, make excess quasiparticles in the qubit junctions. One consequence of that is we'll see an elevated rate for the quasiparticles to tunnel back and forth through the qubit junction, on and off of the qubit island. So we can try to measure that quasiparticle tunneling rate. And we can also see this reflected in an enhanced relaxation rate for the qubits. T1 will get bad for a little while, and so we can also measure that. And now you might ask, what could you do about this? Well, one approach would be to try to just get rid of the ionizing particles in the first place, right? Try to shield yourself from these either muons or gamma rays. It's not trivial to shield yourself from muons. You have to go deep underground, and there are experiments to do that. In mine shafts, say a mile underground. It's not super practical. Not everybody has access to a mine shaft a mile underground. But the gamma rays are even a little trickier because there's all sorts of radioactive contaminants just naturally occurring in concrete that maybe the floor is made out of, or the walls, or even the cryostat itself. And that's tricky to get rid of, and you can only shield so much of that. So that we're not going to focus on the shielding approach. Another possibility is engineering your qubits to try to make them resilient to this process. And that's gotten some traction by several groups recently, doing what's called superconductor gap engineering. So making the superconducting gap very different across the 2 sides of the Josephson junction. That can suppress the tunneling of these quasiparticles that are generated during this process. I'm not going to talk so much about that today, but a third approach, which is what we're looking at here, is to try to mitigate this phonon process, to try to attenuate the spread of phonons throughout the chip, to try to limit the region of the chip that's poisoned after an ionizing impact. And so to do that, we're going to follow an approach that was first suggested by John Martinez back here in this paper a few years ago, which is to put essentially cooling fins on the back of the chip to try to channel the phonon energy away from the silicon so that those phonons no longer have enough energy if they bounce back up towards the device layer where the qubits are to generate quasiparticles in the first place. And so John's suggestion was to do this with islands of copper, so normal metal, copper on the back side of the chip, with the idea that these phonons, as they come in, the phonons that initially are generated going downwards can propagate into the copper. And then when they're in the copper, the phonons can scatter inelastically off a conduction electron in the copper. So the phonons can cool off by heating up the conduction electrons in this copper. And we don't really have to care so much because this copper is half a millimeter away from the qubits on the other side of the chip. And so we've then cooled the phonons off, so when they come back into the silicon, they don't have enough energy on their upwards trajectory to hit the qubits. Or if they do hit the qubits, they don't break pairs. Okay, and I should point out, this doesn't have to be a normal metal. It could be done with a superconductor down here as well, as long as you make the superconductor have a smaller gap than the gap of the Josephson junctions in your qubit. Okay, and so what are different ways we can characterize this? Well, we'd like to be able to produce this poisoning on demand, because it's sometimes a little slow if you just wait for a random gamma ray from the lab to hit, or a cosmic ray muon to come down. So we've looked at several different approaches, and I only have time to talk about one of them today. But we've just to mention them, we've looked at injecting phonons directly using on-chip tunnel junctions. Very recently, we've been working on an optical illumination system where we can use a MEMS mirror that we can steer at low temperatures on the mixing chamber of our fridge to irradiate different regions with about a 100 micron spot of light on the back of the chip and generate this poisoning process. We can also just wait for poisoning to happen, not from ionizing radiation. So this one maybe should have a little asterisk on it, because this is not ionizing radiation, but it turns out another source of this phonon-mediated poisoning can come from just built-up stresses in the chip itself. that relax with earthquake-like events at low temperatures and release bursts of phonons, just like an earthquake at a fault would release ripples of energy that propagates through the ground. What I will talk about, though, are some experiments we've done recently where we actively irradiate the chip with gamma rays, so using a radioactive source. And as I mentioned, we have various things we can look at. So we can track these offset charge shifts. We can look at this quasiparticle charge-parity switching rate. And we can also look at the degradation of qubit T1. OK, and so the chip is not especially fancy. It's just a simple array of 6 uncoupled transmon qubits. These are typically, we make these as charge-sensitive transmons. So their EJ over EC is a little lower than you would normally make if you're trying to make good qubits. But this makes the measurement of these quasiparticle poisoning processes relatively straightforward. And the copper we deposit on the backside of the chip on some of the chips. So we typically make some chips without copper, so we can have sort of a control-type chip. And other ones, we deposit this copper on the backside. You need to make the copper relatively thick to make a difference, because at low temperatures, the electron-phonon interaction is very weak. A lot of the phonon modes have frozen out. So you need a very thick copper there. So we started with 10 microns of copper. We've looked also at 1 micron of copper, and 10 is better than 1. And to get to those thicknesses, we need to electroplate. OK, so this is the experiment. The paper just came out a couple months back. So we use a cobalt-60 radioactive source. It has a fairly high activity. So cobalt-60 emits 2 gamma rays up at around 1.1, 1.2 mega electron volts. And with those energies and that activity, we can put the source outside of the fridge, and the gamma rays will be able to get through all the layers of the fridge, so the vacuum jacket and all the heat shields and the sample packaging, and some fraction of them will then hit our chip. And because the source is outside of the fridge, we can position it at different distances away. So we can change this source to chip distance. And if we assume that the gamma rays are being emitted uniformly into 4 pi solid angle, we can expect that the rate of gammas that are actually going to hit our chip should fall off like 1 over that distance squared, just very, very simply. Right? And so this is the experiment then. We'll be measuring these different qubits on the chip while we irradiate at different doses by putting this gamma source at different locations. OK, and so one of the things I mentioned is we can use the qubits as electrometers. So to try to sense this ionized charge that's generated near the impact site. And this technique is described by a paper between a joint experiment between Robert McDermott's group and mine from several years ago down here. And so this is basically a modified Ramsey experiment where you tip to the equator and you let the block vector evolve. But to make this work, you also need to have one extra knob. You need to have a gate electrode on the chip that has some capacitive coupling to the qubit with an external voltage source, so you can sweep that gate bias. And so if you do this type of modified Ramsey measurement, while incrementing through this external gate bias, you get this characteristic periodic signal that you could easily fit. And if you have then a change in the charge environment that's coupled to the qubit, that gives you an extra offset here. And that shifts this whole pattern side to side. The periodicity stays the same, the height stays the same, but you get a different offset. And so we can repeatedly do this measurement and then track and fit this curve and then extract that offset to look at what's happening in the charge environment that the qubit sees. Okay, and let's take a look at what that happens here. If we do a measurement, say, without the source around and run it for 1,000 seconds or so, we see a few charge jumps over that time period. So let me just orient you. This goes back. This up and down signal here, this vertical axis is the color scale. So these are these peaks, dips, peaks, and we're sweeping this gate voltage along this axis. So we see a jump here, another one here, a few in the course of 1,000 seconds. Whereas now if we bring in our cobalt source, same qubit, looking over the same time scale, doing the same measurement, and it's not even especially close, right? It's 78 centimeters away. Things really go crazy. We get lots and lots of these charge jumps. And so we can go through and fit these slices and pull out a charge jump rate seen by that qubit. And we can then look at that charge jump rate, which is the vertical axis on this plot up here. So we're looking at just how many of these jumps per unit time there are. As a function of, we're going to plot this as 1 over the square of this distance between the source and the sample, again with the idea that we would expect that this should go like 1 over r squared. And indeed, we see this linear dependence here, so that you get the source closer and closer, and the charge jump rate goes up. And we can look at this both for chips that don't have any copper on the backside, which are the chips that we'll plot in red, and also a chip that has, in this case, 1 micron of copper on the back of it. So these two chips were cooled on the fridge at the same time, and you could see they look more or less the same, which is what we would expect, because we wouldn't expect that these copper ions on the back change anything about the electron-hole dynamics in the substrate. They're there to deal with the phonons, not with the charge. We can also see, if we look at these sorts of measurements on multiple qubits on the chip simultaneously, we can see if we look at qubits that are close together, like these yellow ones, are these two qubits here, here, and here, we see a relatively high correlated jump rate where they both see a charge jump at the same time, whereas qubits that are further away, like these other two pairs, are down here, which one of these, let's see, it's these two, and then these two. So they're much further. They're on opposite sides of the feed line on the chip. Those charge jump rates are not so correlated, and they're consistent with just the background random coincidences that you might expect. Okay, so that's looking at the qubits as electrometers to sense the charge jump rates from these gamma rays that were shining on the chip. But now we can also look at the quasiparticle poisoning, and to do this, we use another type of slightly modified Ramsey sequence. This was first developed, as far as I know, in the DiCarlo group in Delft back in 2013, but it's been used quite a bit over the years as a way to characterize quasiparticle poisoning. And here, the idea is you can have the two different parity bands, whether you have an even or odd number of quasiparticles on the qubit island, and this modified Ramsey sequence maps that parity onto qubit one-state occupation. And so if you keep repeating this measurement, this parity measurement, at some cadence, you're either going to get a 1 or a 0, depending on whether you're in the even or odd parity state, so whether or not you have an excess quasiparticle or not. And so you just get this bit string, this random-looking bit string of 0s and 1s, and you can then take the Fourier transform of that and compute a power spectrum, and in general, it looks like a Lorentzian, and you can fit that and pull out this characteristic switching rate for the parity to switch. So if you have a lot of quasiparticle poisoning, this gamma p parameter will be very high, whereas if you have very weak quasiparticle poisoning, gamma p will be very low. Okay, so that's one of the metrics we'll use here to characterize the level of quasiparticle poisoning. And so now we can do the same type of measurements we were doing for the charge sensing, but now we're going to look at this quasiparticle parity switching. Right? So before we were plotting this charge jump rate, here we're going to plot this quasiparticle parity switching rate, still as a function of 1 over the separation squared. And we can see that, okay, they both increase linearly, but now there's a dramatic difference between the chips that don't have any copper on them versus the chips that do have, or the chip, there's not multiple chips, the chip that doesn't have any copper on it versus the other chip that does have this 1 micron of copper on the back side of it. We could see almost an order of magnitude difference in these slopes. This is the same data over here, just plotted on a log-log scale to make it easier to see. So clearly, having these copper ions on the backside, they don't do anything to the charge in the substrate, but they have a dramatic effect on this quasiparticle poisoning, which was, the goal was to try to channel away this phonon energy. So they're doing their job. Okay, and so because we can do both these electrometer-like charge sensing measurements and these quasiparticle poisoning measurements, we can now look for correlations between these two processes. Right? So we can operate one of the 6 qubits on each chip as a charge sensing qubit. So we can operate it in this electrometer mode. And that's the qubit that we've drawn the circle around here. So it's this corner qubit here on the copper chip, and it's this corner qubit here on the non-copper chip. So that qubit, we're going to repeatedly measure its charge and look for these offset charge jumps, which tells us that an impact happened near that qubit. I mentioned earlier on that the typical spread for these electrons and holes is about 500 microns or so, up to a millimeter or so, and that's also about the area that the qubit can sense electric field changes. So if we register a charge jump on the qubit that we're using as an electrometer, that tells us that an impact happened somewhere within about a millimeter of that qubit. If an impact happened further away, that qubit won't sense it through this electric field offset. But then we'll simultaneously measure quasiparticle parity switching on all 6 qubits, including the one that we're using as the electrometer qubit. We can do both measurements on the 1 qubit. And then what we're looking for are correlations where there was a charge jump on the charge sensor qubit and a parity switch on that same qubit or any of the other 5. And these bars then are calculating that probability for there to be a coincidence between a parity switch, meaning that there was quasiparticle poisoning on that qubit, and the one charge sensing qubit that said that an impact happened near that qubit. And what we can see is if you look at the qubit and the parity switching on the same qubit that you're sensing charge with, it's more or less guaranteed to be poisoned, which isn't that big of a surprise. It means the impact happened right underneath that qubit, and no matter how much you try to attenuate the phonons, some of the phonons are just going to go straight up and generate a lot of quasiparticles right there. So we see more or less 100% correlation in both of those qubits that are sensing the charge. But then if you look at the other qubits, if you don't have any of the copper down here to attenuate the spread of phonons, most of the other qubits still have a pretty high probability, and it falls off pretty gradually, even for qubits on the complete opposite side of the chip. But now if we have this micron of copper on the backside, this is very heavily attenuated, right? So when we get over to the other side of the chip, we're down at like 20% or so probability. So the copper really does seem to be doing its job of limiting this spread. And we can now compare this with some modeling, which I won't have too much time to talk about, but just to give you some highlights of a paper we published about a year ago, which is we've worked with particle physicists, in particular dark matter detection particle physicists, who spend a lot of time thinking about background events in their dark matter detectors, and they've developed some very sophisticated Monte Carlo simulation tools for modeling the charge and phonon dynamics in dielectric crystals at millikelvin temperatures. And this is something called G4CMP, and we've now learned how to use it, and we talk to our particle physicist friends all the time. And so this is the basic cascade of processes, and this is I'll describe what this kind of crazy looking picture is representing. So when one of these impact happens, say gamma ray hits the chip, it generates a bunch of electron-hole pairs, but these electron-hole pairs are generally at roughly the same energy. They're all around 3.6 electron volts. And so to figure out how many of them there are, you just have to say, okay, what's the recoil energy? How much energy did this gamma deposit? Let's say it's 100 kilo electron volts divided by 3.6 eV. And so that corresponds to about 28,000 electron-hole pairs that are generated. And roughly about 2/3 of those or so recombine right away, and the rest then spread out. And now what we're simulating here is we're initializing one electron-hole pair at this energy at 3.6 electron volts, just one of them, and we're plotting 5% of the phonons that are generated from that one electron-hole pair that's generated. And it's a ton of phonons, right? They're all over the place. And so to actually get the picture of what happens in a real event, you have to take this picture, multiply by 20, and then multiply by 28,000. So the point is, there's phonons everywhere. You can't get away from them. They're going everywhere. And we can go further with this modeling and actually use it to now model the response of a chip if we have a gamma ray impacting in the center of the chip. And so in this case, we're making sort of pretend qubits, a very dense array of pretend qubits around here, and we're looking at the quasi-particle level in each of these modeled qubits when a gamma impacts right at the center of the chip at various times after the impact happens. And so you can see without copper, and what we're plotting the color scale here is this quasi-particle fraction. So high numbers, red is bad. It means a very poisoned system. And so this spreads, and it stays high at all times. With the copper on here, it's much more attenuated. And I should probably wrap up soon, so let me go fast. But basically, we can apply that modeling and capture exactly the same physics that we measure here between these correlations. And just in sort of the last slide here, I want to say besides quasi-particle poisoning, these impacts can also affect the two-level systems in qubits. And so when these impacts happen, that charge reconfiguration of the substrate can also cause a reconfiguration of the two-level system fingerprint. This was first pointed out by an experiment at IBM just a couple years ago, and it's something we're interested in now. And of course, at CoLab, we're very interested in applying the state-of-the-art fabrication techniques to make the cleanest surfaces and interfaces, to minimize the density of TLS, and to try to make it so that, okay, if you have these impacts happening, they're hard to get away from, you'll have fewer TLS in the first place, so fewer reconfigurations to have to worry about and track. Okay, so let me just put up my acknowledgement slides to thank all the people that have done the hard work on these experiments, and I'll stop now. And yeah, thanks.